Whether you are analyzing survey results, predicting the weather, or estimating public opinion, confidence intervals give us a way to express uncertainty with clarity. This concept is foundational in statistics and widely used across fields like healthcare, business, psychology. In this video, we are going to examine how confidence intervals for proportions work and how to calculate one using the Desmos graphing calculator. Let's start with a quick example about point estimates. A supermarket wants to estimate the proportion of customers that eat a plant-based diet. The supermarket interviews a random sample of 60 customers and finds that 14 report eating a plant-based diet. To estimate the proportion of their customers that eat a plant-based diet, we're going to find the sample proportion. So in this scenario, the supermarket is going to estimate the true proportion of their customers who eat a plant-based diet by asking 60 of their customers. All right, so let's make a proportion out of this data. We know that 14 out of the 60 customers reported eating a plant-based diet. And when we divide those numbers, 14 divided by 60, we get about 0.233, which equals 23.3%. So based upon their sample, they have an estimate for the proportion of their customers who report eating plant-based diets. Now, when we have a proportion from a sample, we call it a sample proportion, and there's a special abbreviation for that. It's P with a hat over it. We actually call it P hat. When we're referring to the proportion from the whole population, we just use the letter P, but without the hat. Now, P hat is called a point estimate. This survey gave the supermarket a rough idea about the proportion of their customers who eat a plant-based diet, but it didn't tell them how precise this estimate is. Fortunately, statisticians have developed methods to add more precision to our estimates of proportions. Before we get to the confidence intervals that will give our estimates more precision, let's pause briefly to discuss simulations. When we conduct a simulation, we are only pretending to conduct a random sample. Even though we're only pretending, simulations are important because they make it possible to visualize what could happen if we actually did repeat a random sample many, many times. Doing so helps us visualize the patterns that emerge when we repeat a sampling process. Not only that, but without diving too deep into the theory behind confidence intervals, simulations can demonstrate that over many trials, a certain percentage of confidence intervals actually do contain the true proportion. Let's take a look at an example involving a simulation, just to get a better feel for what they are. The probability that a visit to the local animal shelter will result in the adoption of a pet is 44%. Serenity wants to know how many visits the shelter will typically need to see to have 2 pet adoptions. She simulated 28 trials of visits to the shelter where each visit had a probability of 0.44, resulting in the adoption of a pet. And in each trial, she counted how many visits it took to have 2 pet adoptions. So she is counting how many visitors need to stop by the shelter before 2 pets are adopted. So let's make sure we understand what these dots mean. So these first 2 dots, they're telling us that in these 2 simulations, the first 2 visitors to show up at the shelter both adopted pets. So it only took 2 visits, the minimum it would take for 2 pets to be adopted. By the way, this number, the 2, it's not going to affect any of the math in this problem. It's just how the simulation is being carried out. So this tallest stack here tells us that the most frequent number of visits it took before 2 pets were adopted was 3 visits. Let's go ahead and calculate the probability. So in this case, P stands for the word probability. So we want the probability that it takes 7 or more visits before 2 pets are adopted. Okay, 7 or more. All right, so here is the number 8. And so these dots here, it took 7 visits for 2 pets to be adopted. And this visit here took 8 visits for 2 pets to be adopted. And then over here we have a trial where it took 11 visits for 2 pets to be adopted. Okay, so let's count up these dots. There are 1, 2, 3, 4, 5, 6, 7 of those dots. It's just coincidence that it's also 7 here. But so of the 28 trials, we're going to assume there are 28 dots here. 7 of those had 7 or more visits. 7 out of 28, that's equal to 1/4, which would be 0.25. Or we could write that as a percentage, 25%. So based upon her simulation, she estimates there is a 0.25 or 25% chance that it will take 7 or more visitors to the shelter before 2 pets are adopted. Let's move on from the world of simulations and look at an actual confidence interval. Researchers asked a random sample of patients if they experienced side effects from a new medication. Based upon the poll, the 95% confidence interval for the population proportion of patients who experience side effects is 0.25 to 0.45. This confidence interval tells us that the researchers are 95% confident, almost certain, but not quite, that the true proportion of patients who experience side effects from the new medication is between 0.25 and 0.45, or between 25% and 45%. Now, the point estimate is in the middle of the confidence interval, which is sometimes obvious just by looking at the endpoints. But when it's not, we can just add the 2 endpoints and divide by 2. The width of this interval lets us know that the methods used to take this sample led to a somewhat imprecise estimate of the true proportion of patients who experience side effects. Now, the margin of error is the distance from the middle of the interval to either one of the endpoints. So in this case, let's go ahead and take the 0.45 and subtract the point estimate in the middle of the interval, the 0.35, to get 0.10. So that's the distance halfway across the interval, or in other words, the margin of error. Now, this is one way to write the confidence interval. So let's make a list of different ways to write this confidence interval. So this is telling us that the true proportion is somewhere in between 0.25 and 0.45. We can also use the point estimate and the margin of error to write the interval as 0.35, the point estimate, plus or minus the margin of error. Now we could use inequality symbols to say that the true proportion P lies in between 0.25 and 0.45, or 0.25 is less than P, which is less than 0.45. And this P is the P that stands for the true population proportion, which is unknown. And finally, we could use the same format but with percents. So we could say the true proportion is somewhere in between 25%, and 45%. All right, so all different ways to write our confidence interval for the true proportion P. Let's read through this situation and create a confidence interval using Desmos. A student polls her school to determine whether the students in the school district are for or against the new legislation regarding school uniforms. She surveys 500 students and finds that 400 are against the new legislation. Construct a 99% confidence interval for the proportion of students in the school district who are against the new uniform legislation. This time, the confidence level is 99%, which means we want to be even more certain the interval we make captures the true but unknown population proportion. Remember, the last one was 95%, which is pretty certain, but 99% is even more certain. So this interval will estimate the proportion of all students in the district who are against the new school uniform legislation. All right, so we have 500 students in our sample, and 400 are against the new legislation. So let's go over to Desmos.com. And we're going to open the graphing calculator. And to get going on our confidence interval, we hit the plus button up here in the top left of the calculator screen. And from there, we choose inference. Okay, now let's think about what the respondents were actually answering. They were answering with a yes or a no. So this was not quantitative data. This was categorical data, where they're not giving us a number, they're giving us a yes or no answer. So what we want is z-test for proportions. All right, there were 400 successes. That's what we call the 400 people who are against the new legislation out of a sample of 500. So we're going to create test. Now over here, we have a choice. We're going to do a confidence interval. And really important, we need to change the confidence level, right? The default is 0.95. We want to change that to 0.99. And we have our confidence interval. Now, sometimes we get more information from these three dots. It tells us more decimal places here for the lower and upper bound, and it gives us a point estimate. And we are not going to use the standard error. That is not the margin of error. So this point estimate of 0.8, well, that's 400 divided by 500. So using Desmos.com, we got a confidence interval of 0.754 to 0.846, or we could write that as 0.8. That was the point estimate, equal to 400 divided by 500, plus or minus the margin of error. And to get the margin of error, we can take the point estimate here and subtract the lower bound to be one way to do that. That's 0.046. So another way to write the interval is 0.8, that's the point estimate, plus or minus the margin of error, 0.046. Or we could even write this as a percentage. Like we could say 75.4% is less than P, which is less than 84.6%. So we are 99% confident that the true proportion of students in the district who are against the new legislation is in between 75.4% and 84.6%. I hope these examples about calculating confidence intervals for a population proportion have been helpful. This is Mr. Ela, signing off.